We talked about the problems of moving data around in memory and from memory to disk. These problems become even bigger when we talk about very large data that you can fit only on multiple machines. So this slide is, this video is supposed to explain how you move data around between different disk file systems and memory, and how you make it into data structures that you can use in the computer memory. The notebook is not intended for you to run on your personal computer. It is just something that is intended for you to see, so that you can, when you're ready to deploy actual clusters, you have a better idea about how things work. And when you use the clusters that we will provide, you know how we prepared things. So some terminology. So when we talk about data that is in memory, we usually think about data structures such as lists or dictionaries or trees. Those data structures allow us to do fast operations of different kinds. This sometimes means that you're storing more than the information content that is needed in order to make manipulations easy. So that is what is called deserialized data. Serialized data is that you take the same data and you just make it into a sequence, and the sequence can be efficiently stored on disk or moved between machines and so on. So a lot of what is going on in big data analysis in the computational side is serialization and deserialization of data. AWS EMR, those are acronyms that describe the system that we are actually using for this course. AWS is one of the bigger cloud providers, Amazon Web Services, and EMR is the part of AWS that is for MapReduce, Elastic MapReduce. Now, if you remember, when we talked about a short history of affordable massive computing, we had a figure like this one, and describing how clusters such as the Google file system and HDFS are constructed so that there is one head node, and then there are worker nodes, and the worker nodes hold pieces of the files in a distributed file system called HDFS. Okay, so EMR, AWS adds another element to this, which is S3. S3 you can think of as the long-term disk storage, right? Usually we think about the disk storage on our laptop as long-term, but we're not so sure that that's good, so we also put it on backup. In AWS, when you rent essentially a computer for a few hours or a few days, it comes with some disk space, and that disk space evaporates when you release the computer and stop paying for it. So you need some place to hold things for the long term, and that is S3. So think about S3 as the place where things are held for long term. Okay, so this is the S3, and from S3 we will usually take the data and put it on the head node, and then from the head node we will want to put it on HDFS in order that the workers can efficiently work on it. Okay, so let's see how all of this is done. So first, to move a file from S3 into the head node, that's a serial to serial movement. What we have here is a command line that is called AWS, that is basically a command line for AWS operations that you can run on AWS machines. And this is specifically for S3, and it says, give me, list for me this file, and it does. It says, okay, I have this file in this location, and this is its size, about 1.5 gigabyte. Then you can say copy from this location to the current location, okay? Copy this all.csv.gz, and that takes 11.3 seconds for this file that is about 1.5 gigabyte. Okay, so it's about 80 megabyte per second. And now we have time to uncompress the file. We uncompress this file and generate the uncompressed CSV by running unzip, and that takes about a minute. That takes quite a while. Okay. And this file is about 7.7 gigabyte. So it's long, it's bigger. But in fact, if we didn't care about storage on S3, we could have stored it uncompressed, and we would have gotten it quicker than using the compressed and uncompressing. Okay, so the next step is to move things into HDFS. Again, this is just serial to serial. And what we're doing here is using the Hadoop command to make a directory to store this information. And then we use the command copy from local, so local means the head node, from all.csv to HDFS, and then we give the address. That's the format. Okay, so that takes about 25 seconds. And now the file is distributed in little chunks on all of the worker nodes, but we don't really have visibility into how it's organized, because that will just be a lot of detail that we don't want to see. So we just see it as a single file. Okay, so if we do ls of it, we see that it's a file and its size is about 7.7 gigabyte. Okay, next we want to read a file into an RDD. Again, it's just serial to serial. We create a Spark cluster, Spark context, and using this Spark context, we basically just say text file weather.csv. The default for Spark context, when we give it the file name, is to assume that it's on HDFS. So we don't need to say HDFS here specifically. And then that, as you see, takes almost no time, because Spark is lazy and doesn't do anything until it really has to. And now we're forcing it to do something. So we're saying RDD count to count how many records we have here. And that takes about 26.2 seconds. If we do it again, we see that it takes just 6 seconds. So even though we didn't explicitly ask for caching here, we still have some level of caching, because it takes much less time to do it the second time. So because we don't want to look at the time that is after you cache things, we want to look at the total time that it would take to do the analysis. We just reopen the file. So now it's fresh, and it will take exactly the same time to read from it. Okay, so now to compare this thing that we have in terms of reading, the speed of reading file, it is an elaborate system, and we basically distributed all the files to all of the nodes, and then we have the nodes read the file in parallel from their different pieces. So it's a very impressive system, but let's see if it does anything for us. So if we look at here is a very simple implementation on the head node, just reading the file, the 7.7 gigabyte file through into memory in the most naive, simple way. And that takes 7.61 seconds. Okay, so that is to say that it is not obvious at all that when you do parallelization, you always win. Sometimes you do parallelization, and what you get as an overhead is so much that it actually was better to stay with just one machine. But when you get to bigger and bigger files, you typically start to see the advantage of parallelization. essentially, when one machine can't hold all of the information in its memory, that's when you hit this boundary, which is not hit here. And if you want to kind of understand more about it, it's useful thing to know that it is important how you compare things, right? So people often just say, okay, we add more and more machine, we get faster and faster, but that is one implementation, and maybe if you did just an implementation on a single machine, you would actually get much better than all of that. So that's just a word of warning when you get into this world of parallel computation. Okay, so far, we just move data around. In the next video, we're going to perform some deserialization. So I'll see you then.